Good morning. Good morning, everyone. I'm Hemming Choi from Columbia. I'm going to talk about a system called Peregrine, which can make multi-threaded programs run deterministically with low overhead, using an idea we created called schedule relaxation. Sometimes the resulting program can even run faster than the original program. For this reason, we name our system after the peregrine falcon, the fastest bird. This work was done with Jin Yue-Wu, John Gallagher, Hua-Yang Guo, and our advisor, Junfeng Yang. As said by Charlie, multi-threaded programs are difficult to get right. A key reason is non-determinism. Different runs of a multi-threaded program may show different behaviors depending on thread interleavings or schedules. This non-determinism actually complicates lots of things, such as understanding, testing, and debugging of multi-threaded programs. For example, testing becomes less assuring because the schedule tested in the lab may not be the ones run in the field. At a language level, non-determinism mainly comes from two sources. The first source is non-deterministic synchronization. Let me show you some examples. So the first example is a non-deterministic synchronization from the Apache web server. Two threads compete for the same mutex concurrently, and then they access a shared memory object. If thread 0 wins, then this program runs correctly. However, if thread 1 wins, then there's a use after free crash. Here, non-deterministic synchronization makes Apache non-deterministically crashes depending on the order of synchronization operation. And the second source is data race. So as you can see in the example, this is a data race from a popular benchmark. In this example, the race on the thread 1 does some computation, and thread 0 prints out the result concurrently. If the race happens as a way on the left, then the printed out result is correct. But if the race happens as an order on the right, the result is printed out before assigned correct value. Now we all know non-determinism is bad. In order to eliminate this non-determinism, researchers have introduced a great idea called deterministic multithreading, or DMT. A DMT conceptually maintains a one-to-one mapping between input and scheduling. As long as input remains the same, these systems always enforce the same schedule to process this input, eliminating non-determinism. Actually, this approach addresses many problems due to non-determinism. For example, testing now becomes more assuring because the schedules tested in the lab are the ones run in the field. To implement deterministic multithreading, existing systems enforce two forms of schedule. The first one is the deterministic order of synchronous operations, such as locks and unlocks and pthread creates. We call them sync schedule. The second one is a deterministic order of shared memory access, such as load and store. We call these forms of schedule mem schedule. Both sync schedule and mem schedule have advantage and disadvantage. Let me further show you. For example, Turn, our previous work, and Condu system, they both use sync schedule to implement their DMT system. For example, these systems always enforce the same deterministic total order for synchronization operations. As long as we enforce the same deterministic order for synchronization operations, the Apache bug always runs deterministically, either crash or correct. A benefit of doing so is efficiency, because most of code actually does not control synchronization operations so that they can run in parallel. However, these systems are only deterministic for race-free programs, but many programs contain races. For example, sync schedule cannot make this data race run deterministically. In order to make data race deterministic, Some DMD systems, such as Cortex and DOS, use mem schedule, which is a deterministic order of shared memory access. These systems always enforce the same order for memory access, as we can see. As long as we enforce a deterministic order for memory access on the shared variable results, regardless of which order we choose, this program always runs deterministically, either printing out correct value or wrong value. But there's a drawback here. Because there can be millions of shared memory access within one execution, and enforcing this order can incur very high overhead. As a result, despite much research effort, an open challenge recognized by the DMD community still exists, picking either determinism or efficiency, but not both. Can we actually get both? Yes, we have built a DMD system called Paragon, which can make multithreaded programs run both deterministically and efficiently. The key insight of Paragon is, although many programs contain races, races only tend to occur within a minor portion of an execution, and majority of the execution is still race-free. Intuitively, if there are tons of races within one execution, then they would have probably been detected in the testing lab. Empirically, we run 6 programs containing races on real workloads. Each of execution contains up to thousands of synchronous operations and millions of shared memory access, but only up to 10 races occurred. I'll show you the more detailed results later. For this reason, we can use a new form of schedule, which we call hybrid schedule. In hybrid schedule, we enforce a sync schedule in the race-free portion of an execution, achieving efficiency. And we enforce mem schedule in the racy portion of the execution, achieving determinism. Because majority of an execution is race-free, so hybrid schedule should be almost as efficient as sync schedule. And because all the data races have been made deterministic, hybrid schedule should be as deterministic as mem schedules. How do we compute hybrid schedules then? In Paragon, we use an approach called schedule relaxation. When the program runs on an input, we first record a detailed execution chase, including memory access, in case the execution runs into races. And then we relax this chase into a hybrid schedule, containing a total order of synchronous operations and a set of order constraints in order to resolve all races deterministically. Then we can reuse this schedule on the same input with both efficiency and determinism. But reusing one schedule on each input is a kind of limiting. Fortunately, hybrid schedules can often be reused across different inputs. We can for example, we can consider PPZip2, a parallel compression utility, which reads in the file, split into multiple file blocks, and spawns a number of threads to compress these file blocks in parallel. We can imagine that as long as the number of file blocks and the number of threads are the same, we can pretty much reuse the same schedule to process different files, regardless of file contents or file data size. Our previous work, the turn system, has shown that the reuse rate for on real programs with real workload can be as high as 90%. But our previous work requires developers to manually annotate input that may affect schedules, which could be time-consuming. In Paragon, we largely automate this process by introducing 2 new program analysis techniques. Paragon runs in Linux. It sits transparent between the application programs and the Linux kernel and the pthread library, simplifying deployment. It works with server programs by using a technique we created in our previous work, Turn. We evaluated our system on a diverse set of 18 programs, including 4 real applications, such as Apache Web Server, and 13 scientific benchmarks, and the RACI, the stress testing benchmark for deterministic execution and deterministic replay systems. 7 of our evaluated programs contain races, and our system is able to resolve all these races deterministically. It's also efficient, and it can frequently reuse schedule on 9 of evaluated programs. Actually, reusing schedules on different inputs can have many benefits. For example, we can compute a set of good schedules that do not contain concurrency errors, and reuse these schedules on a wide range of different inputs so that we can avoid potential errors in unknown schedules. Our previous work turn has shown this benefit. The remaining of my talk contains these 4 parts. First, I will go over the architecture of Peregrine, and then I'll use an example to show how it works, and then I'll present evaluation result and conclude. First, our system contains both compile time and runtime components. At compile time, we take the program source and instrument it. We instrument the common inputs and synchronization operations so that we can check inputs and control the order of synchronization operations at runtime. Our instrumenter works on the LLVM compiler framework. At the runtime, a key module of Peregrine is the schedule cache, which stores a set of tupules. Each contains a hybrid schedule, S, and the preconditions, C, that must be satisfied in order to reuse this hybrid schedule. When a new input comes, the system will first check the input against the preconditions in the schedule cache. If it couldn't find such preconditions that can match this input, then this input is simply forward to the recorder module. The recorder will run this input on the instrumented program and record execution chase. The chase contains synchronous operations and memory access. The chase is for computing hybrid schedule and preconditions. The analyzer module, the most challenging to build component in our system, read in each chase and compute a set of tupules containing the hybrid schedule and its preconditions and insert it to the schedule cache. Further, when a new input comes, and if we can find a precondition that matches this input, then this input is simply forwarded to the replayer module with the hybrid schedule. Our replayer will enforce the hybrid schedule on this input, making the program run with both efficiency and determinism. All the components in our system are shaded. This may sound too abstract. Let me use an example to show how it works. This example comes from real programs, such as PPC2 in our evaluation. It first reads in 2 command line arguments, the number of threads and the total size of data. It then enters the loop to spawn the number of threads. Each thread will call the worker function as the thread routing. In the worker function, it first allocates a piece of memory from heap, and then it enters the loop to perform computation. During the computation, it reads in file from a disk and do the computation. The detailed computations are not shown for simplicity. Further, it grabs a mutex and updates the shared variable result. And the main function also calls the worker function to do computation. It then optionally updates the shared variable results based on the 3rd argument. And then finally, it prints out the results. This is how this code works. But there's a bug here. The pthread join is missed by the developers. So there's a data race between the main thread and the trial threads on the shared variable results. Given this code, our system first instruments all the command inputs automatically. The command input contains input command arguments and read function calls, and more. Please refer to our paper for more details. And further, we instrument all the synchronous operations so that we can control their order at runtime. After the instrumentation, let me show you how we record execution chase. On this input 220, it means the number of threads 2, the total size of data is 2, and the 3rd flag, which is control flag, is 0. First, the main flag will read into command arguments as shown in the source code, and then it enters the loop to spawn the number of threads. The shaded area on the left is the loop to spawn threads, and the shaded area on the right is the instructions and conditionals generated during the computation of the loop. Because the index I starts from 1 and n thread, which comes from input, is 2. So the p thread creates is called only once. And then there are 2 conditionals generated. The first conditional is one smaller than n thread with outcome true. Because when the for loop is executed first time, the true branch of the for loop is taken. And similarly, there's another conditional saying 2 smaller than n thread with outcome false. Because when the for loop is executed at the second time, the I becomes 2. So the fourth branch of the for loop is taken. Then a try flag is born. It allocates memory and performs computation. And similarly, 2 conditionals are generated. And concurrently, say the main thread also does the computation. And then it updates the shared variable. And the try flag also updates the shared variable and exits. And finally, the main thread will check against a control flag and print out the final result. This is the execution trace we collected from the input 220. Given this trace, I will show how we compute hybrid schedule. First, we extract a total order of synchronization operations from the trace and add it to the hybrid schedule. You enforce a total order for all these synchronization operations at runtime. And also know that there's a data race happening during the execution on the variable result. And we does the race detection on this trace. So the first access and the second access on the variable result has a race because the log is not deterministic as the log contention is non-deterministic as I just shown in the example. And also, there's a race on the second axis and the third axis. But after we enforce a total order of synchronization operations, the synchronization non-determinism is removed. So the race on the first and the second variable is already resolved deterministically. So now we only need to consider the second and the third axis. We add it to the hybrid schedule, and then we enforce order constraint to resolve this race deterministically at runtime. Now the hybrid schedule is computed for this program, for this execution. It contains a total order of synchronization operations, such as pflag create, lock, and unlock. And then it contains one order constraint to resolve the race deterministically. Given this hybrid schedule, next I will show how we compute preconditions. There are 2 challenges in computing preconditions. First, once the input matches the precondition, we need to ensure that the hybrid schedule is feasible for this input, which means that all the events in the hybrid schedule must be reached for these new inputs in the new execution. For example, if a new input comes and it requires 3 threads, then obviously this schedule cannot be used by the new input because it only contains 2 threads. Second, we need to ensure when we are reusing schedules on new inputs, there are no new races running up. For example, the main thread at runtime, you check against the third argument. If this 1, then it updates the shared variable results. Otherwise, it will not update the results. During the recording, the third flag is 0. So there's no problem here because the main thread will not update the shared variable. But if we reuse the schedule on new inputs, if the third argument becomes 1, then the true branch of the if statement is taken. Then there's a new race coming up. We want to avoid this because if there are new races, then the new execution becomes non-deterministic. A naive approach to solve this problem is just to collect all the conditionals generated from all the branches that depend on inputs. For example, in this case, the n thread and size and the flag, the 3 variables all come from inputs. So we collect all these conditionals generated from this execution, and we try to simplify them. Let's look at the first two conditionals. It's saying n thread must equal to 1, and n thread must bigger than 1, and n thread must not bigger than 2. It implies that actually n thread equals to 2. So our system actually simplifies this constraint into this form. It's saying n thread equal to 2, size equal to 2 and frag is not equal to 1. That's what we learned. That's the condition what we learned from this execution. But actually, there's one problem if we compute the precondition in this way. Although this approach is reasonable because it ensures that if a new input satisfies all these preconditions, we try the program go down the same execution path. But it has a problem because it over-constrains the data size. The data size is fixed at 2, as we can see. But if you look at where the condition comes from, it actually comes from the computation loop in the worker function. Actually, regardless of data size, we can actually reuse these schedules on different inputs. I will show you later. So we can see this constraint, size equal to 2, is unnecessary. Ideally, we want to remove unnecessary conditionals from our preconditions so that we can frequently reuse schedules. But the question is, how do we know which conditionals are necessary, which are not? This turned out to be a very hard problem and cost most of our effort in the project. We created 2 new program analysis techniques in order to solve this problem. I will not go into the details of these techniques in this talk. Please refer to our paper for more details. I'm going to present the final results in this talk. The basic idea of our techniques is trying to identify all the very local computation and remove these instructions and their conditional from the chase so that we can remove unnecessary constraints and we can get a wider input range for a hybrid schedule. After we apply our techniques, the computation loops have been removed from the chase. And there are only 3 conditionals left in the chase, and we further simplify them to be n flag equal to 2 and flag is not equal to 1. Now we have computed the hybrid schedule and the preconditions to reuse this hybrid schedule. Let me show how we reuse schedules on new inputs. Say we have a new input coming with number of flags 2, data size 1,000, and control flag 3. Because the data size constraint does not exist anymore in the preconditions. So actually, the data size does not matter for these preconditions. And the number flag and the control flag can all satisfy these preconditions. So program simply reuse this schedule on these new inputs. There are many benefits of doing this. First, we can deterministically resolve races on the execution when running on the same inputs. Even there are races on the shared variable results. And we do not have any constraints, execution order constraints on the computation loop. So these loops from different threads can run in parallel. So we didn't sacrifice much performance. And we can have a wide input range for this hybrid schedule because the data size and the contents are not constrained in the preconditions. And there are other applications using our techniques as well. Feel free to talk to us after the talk. Next, let me present the evaluation results. We evaluated 18 programs with our systems, including the Apache Web Server, the PPZip2 parallel comparison utility, the AGET parallel file downloader, PFScan parallel file scanner, and 13 scientific benchmarks, and the RACI, the stress testing benchmark for deterministic execution and replay systems. So here typically, we chose this workload, and typically a larger file or larger workload will mask the overhead of our system. We used an 8-core machine with 8 threads to do all the evaluation. Let's first look at determinism results. So 7 of our evaluated programs contain races, and they contain 2 real applications, Apache and PPZip2, and 4 scientific benchmark, and the RACI benchmark, which contains tons of races. From the race detection results, we can see that except RACI, both the 2 real applications and the scientific benchmarks have very small number of races occurred. This actually matches our insight that race rarely occur within one execution. And enforcing And enforcing deterministic order for these races actually will not affect performance much. And if we only enforce a single order, we learn from the hybrid schedule. We are only able to enforce determinism for 2 of the programs. By enforcing sync hybrid schedule, we are able to resolve all these races deterministically. Let's further look at the result on reducing schedules. This is the overhead from the replayer module. We run the program deterministically by enforcing our hybrid schedule in the replayer, and we compare the performance against the non-deterministic execution. This way is critical, most performance critical, because the replayer module runs in the deployed program. We evaluated the 4 real applications and the scientific benchmarks, and for 5 of them, we incur a significant speed up due to an optimization technique we introduced. Please refer to our paper for more details. And for 9 of them, the overhead is less than 10%. And for 3 of them, the overhead is up to 50, because they perform a big number of synchronous operations within a small number of time. But this number is still smaller than the existing DMD systems that are enforcing MEM schedules, which have both the determinism with our system. Next, we look at the effectiveness of our program analysis techniques. So basically, we want to remove unnecessary constraints so that we can reuse schedules on a wider range of inputs. And we measure the number of instructions left in our chase after we apply the techniques. The y-axis shows the number of instructions left, the percent of instructions left. The smaller the portion of instructions left, then the more effective our techniques are. And the more constraints we can remove from the chase, and the more frequent we can reuse schedules on different inputs. For 5 of them, the chase size is actually smaller than 20%. And for 9 of them, and for 5 of them, the chase size is between 20 to 50. And for 3 of them, the chase size, the slice size left is more than 50%. Next, let me conclude. By leveraging the insight that race rarely occur, we combine both the determinism of MEM schedule and efficiency of sync schedule, getting the best of both worlds. We use an approach called schedule relaxation to compute hybrid schedules. Evaluation results show that it is deterministic, efficient, and stable. And our techniques also have broad applications, which we will explore in the future. That's all my talk. Yeah, thank you. Any questions?
Questions?
Christian Zanferi, PFL. It seems to me that you really need the inputs to be provided in the beginning of the program. What happens, for instance, if you need to decide afterwards and there's a program that continuously reads input? And actually, I'm surprised because PBZip also has the input, the file, and it constantly reads it in a loop. So how does it work in that case?
So your question is, if input comes continuously, how
Right.
do we handle? Yeah, so actually, in our implementation, the input can come in continuously. For example, you don't have to read in one input at one time in the command line. You can read in gradually with for example, the read function at the beginning of at the middle of the execution. So our previous work turn has already solved this problem by implementing the schedule selection as a decision tree, and so that it can read in input at the middle of execution gradually, and then do a decision to choose which schedule to go forward. Please refer to our previous work for more details.
Okay, but that also means that you will have overhead proportional with a number of memory accesses for which you have to check whether the schedule can be reused, right?
Yeah, I don't quite get your question. Please repeat, please.
So you will have overhead proportional to the number of memory accesses that you would have to check in order to see if you can reuse the schedule if the input matches the condition, right?
Your question is, so if we have more memory access,
Right.
then we have to check more inputs in the. You have to check more inputs in the
Yeah, that's it.
preconditions. So let me think about, yeah, okay.